Topic 8C, multivariable optimization. So in this lecture, we're going to delve into some new mathematics that involves some pretty sophisticated vector calculus. And honestly, I think that's beyond the scope of this class, so we won't go too deep into it, but I will mention some stuff and do my best to explain it more just to give you a taste of what it's like. The other thing you'll notice is that you'll see this multivariable optimization very often is based on the 1D optimization. So let's go ahead and dive into this. We will discuss some mathematical preliminaries. I want to talk in general about multivariable functions, talk about scalar vector fields, gradients, and a new concept called a Hessian. And then I want to revise the derivative test when we have multiple variables. Things change a little bit. Then the methods we'll discuss. We'll talk about Powell's method, gradients and Hessians, Steepest Ascent method, and then finally we'll look at Newton's method for multiple variables. Okay, let's dive right into this. Our mathematical preliminaries. So multivariable functions. This could be as simple as instead of just having x, we have x and y, or x and y and z, or x and y and z and alpha and beta and gamma, and so on. So rather than write all these different variables, we'll just write x1, x2, x3, and that will generically represent multiple variables. So we can write this simply as f with an x bold in this input argument, and that x bold is a column vector of all the different variables that f is actually a function of. Writing it this way, showing all these different variables, well, that's nice if you only have 2 or 3, but suppose you actually have 10 or 20, and that can happen. We don't want to write it that way, so just f with a bold x is the way we prefer to write that for multivariable functions. Our equations are more compact, and I think they become a little bit easier to understand. So just as an example, suppose we have just a 2-variable function. We could write it as f bold x, and inside this bold x is just x and y. So this first equation is how we would normally write it, and then down here is in our new notation. Another example, let's break away from the xyz thing, and we have a Gaussian. So it has an amplitude, it has a standard deviation, it has a value of x, and we can put all of these again in this bold x column vector and just write it as f with the bold x column vector. So let's get comfortable with that notation because we will be using it. We'll also be talking about vectors because we'll be calculating gradients and moving in the directions of gradients. So talking about scalar and vector fields is useful. So a scalar field, by field this means it's a function. And so here I'm just showing something that's a function of x and y, so it's a planar picture. And if it's scalar, that really just means we have a single number associated with every point in that function. Just a single number. Think of it as like cloud density. And so that's not a vector phenomenon, it's just the density of the water droplets as a function of position around a cloud. Now that's different than a vector field. Field again means it's a function of multiple variables usually, but at each point there's 2 pieces of information now. It has what the scalar field had, and that will be the magnitude of a vector, but there's also a direction. Back to the cloud example, maybe rather than the density, maybe we're looking at the velocity of the water droplets inside the cloud. So different parts of the cloud as it's moving and bubbling and whatever clouds do, each of those water droplets are moving in different directions and they have a different speed. So the speed would be the magnitude and the direction they're moving will be the direction of the vector. And so we usually draw vector fields as just a whole bunch of arrows where the length of the arrow conveys the magnitude and of course the direction conveys direction. So that's the difference between scalar and vector fields. Isocontour lines. So we form isocontour lines in scalar functions, and we draw those lines along where that scalar function has the same value. So think of this as a topological map where it's mapping altitude of the terrain. If you were to walk along one of those isocontour lines, you would not be going up or down. You would stay at the same elevation. Then we can think about the gradient. And we take the gradient of a scalar field. So here we start with some scalar field, and we calculate the gradient of it. When we calculate the gradient of a scalar field, we get a vector field. And that vector is always pointing uphill. Now, it's not a smart map. It's not like it looks macroscopically over everything, figures out where the maximum value is, and point in that direction. Boy, that would be useful if we had that, but we don't. Going back to the elevation analogy, if we calculate the gradient, it's like you're staring straight down at your feet and you're determining which way is uphill just by looking at your feet. So the gradient is a very local assessment of which way is uphill, but the arrows point uphill, but very locally. And so to point out an example, let's say we're standing right here where my little laser pointer is. The top of the peak is over here, but notice the arrows are not pointing in that direction. They're just pointing very locally where my feet are of what's the steepest way to go uphill. Now, we always hope that that is in the general direction of the top of the mountain, but not necessarily. Okay, so the gradient of a scalar field gives you a vector field that points locally uphill. We can then also draw our isocontour lines on this. So we're looking at a bunch of stuff at the same time. The red in the background is the original scalar field. The arrows are the vector field, which is the gradient of that scalar field. And then the isocontour lines of the scalar field. So one thing we'll notice here is those arrows, the gradient is always perpendicular to those isocontour lines. That makes sense. In the direction of those lines, the elevation's not changing at all. So it makes a little bit of sense that the maximum or the direction of maximum change would be perpendicular to that. So all of this stuff is related and useful when we're thinking about optimizations. Because when we're optimizing, we're always going up and down hills to try to get to the peaks or the valleys. So when we have multiple variables, we have a multidimensional gradient. And so for x, y, z, this is probably an equation that you've seen before. This comes from vector calculus. And essentially the x component of the gradient, we take that function, take the partial derivative with respect to x, and we point that far in the x direction. Then we take the partial derivative with respect to y, and we point that far in the y direction. Then take the partial derivative with respect to z, and we point that far in the z direction. And all components together, that's pointing in the direction of maximum change. Now, when we have many multiple variables, maybe we have 10, it becomes very difficult to imagine a 10-dimensional space. And so at some point, we really just stop trying to picture that, and we just go with the math. And so we're using this bold X, which contains all of our independent variables. But it's essentially the same thing. We're taking the partial of all those independent variables with respect to x1, and then the partial with respect to x2, and so on. And we go through all of the independent variables. So that's our gradient in n dimensions. So let's just review some of the properties of the gradient. First, it only makes sense to calculate the gradient of a scalar field. Now, I put a little asterisk note here, and this is not something we're going to talk about in this class, but in fact, we can calculate the gradient of a vector field, and it turns out we get a tensor. It's called the Jacobian, and this comes up when we do coordinate transforms, and not something I want to get into, but I guess I just felt weird saying that you can't take the gradient of a vector field when I know that we actually can. So for this class, let's just go ahead and say that. It only makes sense to calculate the gradient of a scalar field. When we do that, the gradient points in the direction of the maximum rate of change in f. This means it's pointing uphill, but locally uphill. We also notice that the gradient is always perpendicular to those isocontours or the constant f surfaces. And we also notice that the gradient always points towards the big positive numbers in the scalar field. So it always wants to go uphill. So those are the properties of the gradient, and we're going to use this to try to seek out the maxima or minima in multiple dimensions. Now, a lot of times when we're doing optimization, we don't have access to closed form equations. In fact, I would call that sort of rare. We're much more often processing numerical calculations that come about due to simulations or something else like that. So if we don't have closed form equations, how do we calculate these derivatives? Well, we can use finite differences, and we just finished that, so we'll be very good at that. We can evaluate the function at two adjacent points, divide by the spacing, and now we've estimated the derivative in that direction x1, and we can do this for all of our independent variables. Now, if it takes a while to evaluate f, this can be a very expensive computation to calculate the gradient, but we don't really have another choice. So other than when we develop our optimization algorithm, pay a lot of attention to minimizing the number of iterations. Now let's think about our derivative tests in multiple dimensions. So when we did 1D optimization, when the first derivative was 0, that was an extrema. And then we could look at the second derivative and figure out whether we had a minimum or a maximum. But let's say we have two variables now, x and y, and let's say both of the second order derivatives are less than 0. Does that mean we have a minimum? And in fact, not necessarily. And so the graph that I'm showing here, borrowed from the textbook, think of that as being shaped like the saddle on a horse. And so, in fact, they use that analogy so much, if we were to look at the very center of the saddle, right where your butt would sit down, we call that the saddle point. And if we're sitting at the saddle point, if we took those two partial derivatives, both would be less than 0. However, we can look at that and know that we're not at an extrema. So we could move either of these directions and get to a lower point, or move in this direction and get to a higher point. So that saddle point, even though both of the partial derivatives are less than 0, does not mean we're at an extrema. So we have to throw out those derivative tests and think of what to do differently. And that's where this concept of the Hessian comes in. So we can think of the Hessian as our revised way of exploring curvature in multivariable functions. And we can use this to actually determine if something has a maxima or a minima. So the Hessian has this crazy definition, and we're writing just a Hessian of f. So to help make this a little more sense, here's the Hessian just for a two-dimensional function. And that could make a little bit more sense. So the determinant of the Hessian is simply these two, the product of these two terms minus the product of those two terms. So that's our determinant, and the Hessian is simply our multivariable version of exploring maxima or minimum. It's our multivariable version of curvature, if you will. So here's our revised derivative tests. If the determinant of our Hessian is greater than 0, and then we also look at one of the partial derivatives. I'm showing the partial with respect to x here, but that could be partial with respect to y. So if the determinant of the Hessian is greater than 0, and the second order partial is less than 0, we're talking about having a local minimum. Similarly, if the determinant is greater than 0, determinant of the Hessian is greater than 0, and the second order partial derivative of either x or y is greater than 0, we have a local maximum. If the determinant of the Hessian is less than 0, then we're at a saddle point and it's not a local minimum or maximum. So our extrema occurs where the determinant of the Hessian is greater than 0. Once we know we're at an extrema, then we can go back to our second derivative test and determine whether it's a minimum or maximum. So that's how we use the Hessian to do this. And this will come up again when we talk about the Newton's method for multiple variables. There's also the concept of a conjugate direction. So let's say we have a two-dimensional function, and what I've done is draw the isocontours so we can sort of visualize moving uphill to the maximum. But we don't know where that maximum is. And we might take two guesses as to the maximum over here. So we'll take two guesses as to where the maxima could be, and we'll pick a direction. And the direction is shown by these red lines. So what we can do is, starting with this guess, we can perform a one-dimensional optimization in that direction. And when we get to a local extrema, we end up here at x1. Easiest to visualize it as a maxima, I guess. Then we go to our second guess, do a 1D optimization in that same direction, and we end up at x2. Then if we draw a line that passes through x1 and x2, it turns out that will pass through the extrema. And if this is a quadratic, that would be exact. Now, we rarely have a perfect quadratic, so it will rarely go exactly through that direction, but it gives you a very good estimate of that. And that direction that we construct is called a conjugate direction. There's another way. We could only have one guess, XA, and we pick two directions. And we perform a one-dimensional optimization in the first direction, a one-dimensional optimization in the second direction, and then if we find those two extrema, the line passing through those 2 points is also our conjugate direction. So there's multiple ways we can come up with this conjugate direction, and it's really neat, though, that it's a really good way to point to where the local maxima could be. And for a quadratic, it's exact. Rare we have an exact quadratic, but normally the closer we get to an extrema, the more quadratic it looks. It's only when we're far away that that doesn't work so well. Okay, boy, we went through a lot of stuff. So on to our first search, and this is probably the simplest and most obvious, but then of course it's the least efficient. So let's talk about the univariate search. So in the univariate search, what we do is we optimize one variable at a time. So for example, we might have a starting point and we optimize in the direction of x2. Then we move on to x1, optimize in the direction of x1, then optimize in the direction of x2, then x1, and so on, and we march our way there. So if we have multiple variables, let's call it A, B, C, and D, the first thing we'll do is do a 1D optimization, just adjusting A till we get an extrema. Then do a 1D optimization on B to get to an extrema. Then C, then D, and then back to A. And we just keep iterating through this. And sort of in this stair-stepping manner, we approach the extrema. So that's probably the simplest and most obvious way. It's definitely not the fastest because we're not using things like conjugate directions and stuff like that. It's very robust, very simple. It does work, but not the most efficient. There is something that folks sometimes call the pattern direction. So if we're doing this univariate search, we can start to see an overall trend. And in fact, if we start at some point and we look at the progression of points, they're pointing towards the maxima. And if we look at this second point and the fourth and the sixth, they're pointing towards that maxima. So those are called pattern directions. And very often you can start and do this for a few iterations, develop the overall direction, and then maybe make a larger step in that direction. And there's other ways we can use the pattern direction. Okay, on to Powell's method. This is a very efficient method, but I think you'll also see it's a little strange, and this involves concepts of conjugate directions. And for curves that are exactly quadratic, this actually converges in just 2 iterations. If not, it may take a few more. Okay, so we start off with a guess, and we'll pick 2 different directions. We will then do a one-dimensional optimization along that first direction. So that takes us from our first guess to this revised point x1. From there, we'll do a 1D optimization in our second direction. And that brings us to an h2. Well, the line connecting x0 to x2 is a conjugate direction. And we're not exact right here. So, but we can do now another optimization in that direction h3. So we do a 1D optimization and we're starting to get closer. At this point, we sort of pretend that x3 is our original x1 and we do everything all over again. So we'll do a 1D optimization in the direction of h2, and this gives us our x4. We'll then use that previous conjugate direction, do another 1D optimization along that, and we get an x5. And then between x3 and x5, that line is another conjugate direction. And if this were a quadratic, we'd be exactly on the maxima. If it's not a quadratic, but just something close, we'd be really close, and you can imagine repeating this. Okay. So here's the summary of the algorithm in 9 steps. We pick a starting point and 2 different directions. Then we start at our starting point and we do a one-dimensional optimization in that first direction. And we find extrema x1. Then we do another 1D optimization starting at x1 in our second direction. So we find the extrema x2. Then we define a third direction, which is the line connecting x0 to x2. You can think of that as our conjugate direction, and that takes us hopefully to closer towards the maxima. And then we sort of do this all over again. Slight change, but starting at x2, we do a 1D optimization in the conjugate direction. Then at x2, we do a 1D optimization in that second direction to find an x4. Then from x4, we do a 1D optimization along the third direction to find an x5. And then we have our conjugate direction connecting x3 to x5. And then we do a 1D optimization along that conjugate direction to find the extrema. That's Powell's method. Very fast, very efficient. A little bit weird though, maybe. So because this is exact for quadratics, we call it quadratically convergent, and it'll converge in a finite number of iterations to an exact value. And most functions, and most of the times you're running optimizations, it won't be an exact quadratic, but normally the closer you get to one of those extrema, the more quadratic it looks, and in fact, the better these algorithms will work. So these algorithms tend to go unstable when they're started far away from the extrema. So it's really up to you to try to get a very good guess to start with, because these algorithms will work better if you have that good guess. Okay, our next method, the steepest ascent method. So let's say we have 2 variables, x and y, and I plotted our function and also plotted the isocontour lines. How do we find the maximum? Well, visually, we know it's right here. But, mathematically, we don't know that. So we have to start somewhere close to that and let the algorithm refine this. So we make a first guess, and we'll call that point x1. And so if you saw it, it appeared out here. So we have a starting point. Then we'll calculate the gradient. So remember what the gradient does is it points locally uphill. So if I'm sitting at this point locally, this is the direction of uphill. It's not the right direction. We really should be going this way, but we don't have information about where the extrema is. All we can do is move in the direction of the gradient. So let's do that. Let's move in the direction of the gradient. Question is, okay, we can move in that direction. How far do we go? So we can write a general expression. We can say our second point is our first point plus some constant multiplying the gradient. So that means we're going to move in the direction of the gradient scaled by some constant alpha. And we can use that alpha to slow down our steps. We're making smaller steps or make those steps bigger. Bigger steps, you'll see, we get there faster, but they can go unstable. Smaller steps, it's more stable, but we converge slower. So where's the magic number for alpha? There's no way we can answer that. What I can say is when I'm trying this method on a new function for the first time, I'll pick a value of something like 0.1. But that's no guarantee that that value is going to work for you. And you'll see that. Well, I have some animations and stuff that will illustrate the effect of alpha. Okay, so we've moved some distance. We calculate the gradient again. Now we have a new direction to go in, and it looks a little bit better. It's pointing a little bit more towards the maxima. And so we advance again. And this will repeat. We'll calculate the gradient at the new point, move in the direction of the gradient. Recalculate the gradient at the new point, move in the direction, and just keep doing this. Now, something weird kind of happened. The gradient, if we're at a very, very steep point, will be huge. And so even if we picked a smaller value for A, our new point could be way past where that maxima is. And even worse, maybe even put us on a different maxima that's not as big as this one. And so our algorithm has jumped extrema, and we could end up finding the wrong one. So we want to make alpha small enough so this doesn't happen. We don't want to go unstable. We don't want to skip over our function altogether. So the choice of alpha is important. So here's the algorithm. And step one, we pick a starting point. And hopefully we get a pretty good guess of the starting point. The better your guess, the better this algorithm will work. Then we calculate the gradient at that starting point. At this point, we can check. If that gradient is 0 within some tolerance, that means we're at an extrema and we're done. If not, we want to move in the direction of that gradient, but scaled by this variable alpha, which we'll talk more about in a little bit. Another little tweak to this algorithm, rather than move in these small increments in the direction of the gradient, what if you did a one-dimensional optimization in the direction of that gradient? And in fact, we can improve the steepest ascent method that way. Then we go back. So we move our point, recalculate gradient, move in that direction, recalculate the gradient, and do this over and over and over. That's the steepest descent method. So here's an animation of this optimization choosing alpha equals 1. And what we can see is that it's going unstable. And in fact, this never would converge. It's hopping back and forth because the steps are just too big. And if you're plotting your results, if you're visualizing results, it's pretty easy to see that this is happening because it's jumping all over the place, as instead of just one nice smooth path, as you'll see later when we have smaller values of alpha, it forms a nice smooth path immediately to the extrema. Okay, so 1's not working. It's too big. Our step sizes are too big. Let's pick a value of 0.5. Well, it still looks unstable, doesn't it? Maybe a little bit better, but for the most part, still unstable. So that choice is too big. Let's go to a smaller value. Let's do 0.25. We can see that the steps are smaller, so maybe it would converge slower. But the others didn't converge at all, so I guess that doesn't make much sense. Now this time it looks like it's converging on that answer. And it converged pretty quick. So we're taking pretty large steps. But you know, maybe we're on the verge of being stable or not here. Let's pick a smaller value. Let's pick a value of 0.1. And usually when I implement this method, before I really know anything or try anything, my first guess will be a value of 0.1. And what we see is a nice smooth path to that extrema. And that's really what we should see. And that's the sign of a healthy optimization. So a value of 0.1 here works pretty well. What if it were smaller? Let's do a value of 0.01. Well, holy smokes, look at how small those steps are. We're pretty sure this is going to be a very reliable way to get to that maxima, but man, this is going to take a while. So we'll go ahead and let this run. As we approach the steeper part, where the isocontour lines are tighter, it will speed up a little bit, but this is the drawback that you give up for stability of the time. This definitely takes a lot longer to converge. So I would conclude from this that a value of 0.01 is too small. Now, if your function behaves rather crazy, you might just have to use small values like this. It's just something you have to get a feel for when you run it. That I know of, there's no way ahead of time to know what value of alpha will guarantee that you find the extrema. It's just something you'll have to try. So this is taking a really long time. I'm trying to say stuff to fill the time, and now I'm running out of stuff to say. So we'll just go ahead and let this run. Notice the increments are a little bit larger here, simply because we're working through a steep part of the function. So the gradient's larger. But it'll get smaller again as we approach the top and the gradient becomes smaller. But notice how direct of a path this took. It may take a while, but it's a beautiful curve to take you to the extrema. Now we can see the gradients getting smaller. Those little red or pink arrows are becoming smaller and smaller, telling us that the gradient is smaller. But we will eventually fall on that extrema very reliably. Now maybe this is a good thing to do if your function evaluation is very fast. Maybe it's just a closed form equation. But if it's a simulation or something more expensive, I think it's worth investing the time to come up with a more optimal value of alpha. And to stop the algorithm, we're always looking at the gradient. And when the gradient is 0, meaning we're at a flat spot, that's the top of this function, we know that we're done. Okay, so we went through that. We invested the time and we saw it. Let's do an example of this. Let's say we have this function here. It's a function of x and y, and we have it within this 2D space here. So we've limited values of x and y. Where is the maxima of that function? We can do a crude plot and estimate where it is, and this will let us make an initial guess. So let's just pick a value of 2 for x and a value of 0 for y. That'll be our first guess, and maybe you saw this little dot appear here. So that's our first guess, and we want to proceed with this. So we need to calculate the gradient, and in this case we have a closed form equation, so we can actually come up with a closed form equation for the gradient, which is what I've done here. And so the final answer is here, and we can use this expression to calculate the gradient at any point. Well, we have a point. We have our first point. So we throw the numbers for our first point into that expression for the gradient, and we've calculated a gradient. So, and that has a direction, and I've plotted that over here. Here's our first guess, and here's the direction we want to move. And we can see it's not pointing exactly at the peak, but in that general direction. So we want to move in the direction of that gradient. And we also check the magnitude of the gradient. It's not 0, so we're not done. If it was 0, that means we're sitting at the top and we're done. So we have our values of x in a vector, and we have our gradient. And let's choose a value of 0.1 because that's usually my favorite value. And so we calculate an x2 as our first guess plus alpha times the gradient. And that gives us an evaluation of where our next point's going to be, and that's right here. So we've done what we talked about before. We make a guess, we calculate the gradient, and we move along that gradient. Okay, now we evaluate the gradient at the second point. And then guess what we'll do? We'll move in the direction of that gradient. And we keep doing this. And in this case, after 77 iterations, I finally converged to where the maxima was. So a value of 2 for x and a value of 1 for y, and that sits us right at the top. So, all right, that's it. That's all it is for this example. Newton's method for multiple variables. This is where we'll use the Hessian. Remember what the Newton's method was for 1D optimization. It was essentially the Newton-Raphson method where we did root finding, but we're root finding on the first derivative. So for multiple variables, we change this a little bit and we'll make use of the Hessian. So for multiple dimensions, we can write a second order Taylor series for that function evaluated at x. Remember, this bold x contains all of our independent variables for any number of dimensions. So our second order Taylor series now looks like this, and this is where the Hessian appears. So let's remember how to interpret that. We are estimating our function value at x based on known numbers at some other position x. So we're just calling position xi. And so we could essentially do all this math at our position x and get an idea of what the function is valued at x based on what happens at xi. So that's the Taylor series. Now at an extrema, the gradient goes to 0. So we can take this equation for f, which is the second order Taylor series, and calculate the gradient of it. And it simplifies down to this. So guess what we'll do? We'll set that equal to 0. So that's what happens. We set this gradient equal to 0, and then we solve for x in terms of xi. And this gives us this small little update equation. So given a previous guess xi, we can calculate a new guess as to where the extrema would be. We're moving in the direction of the gradient. Since we're in multiple dimensions now, we're using the Hessian, the inverse of the Hessian actually. So there's our final update equation for Newton's method for multiple variables.